Hello everyone, this is week 7 Wednesday and we'll be working on integer programming, which is part of linear programming. We'll denote it with IP, and there is different kinds. We can have one that all the variables are integers, some that are mixed, so some integers and some just real numbers, or we can have binary 0-1 IPs. So let's start with the first question. And for this one, we realize that the LPs are more relaxed than the IP. And we'll see that in the following example. So we have to maximize z equal to 21x1 plus 11x2. That is subject to 7x1 plus 4x2 less or equal to 13, but we want our variables to be integers. So I plug this in into Desmos, and now we're gonna see how our function, I called it z, how it changes depending on the variables. So our z, I put a slider to change its values, and I'm moving it just to see where we have its maximum value as of right now. I'm looking at all the values, not just at the integers. So we have a candidate right here at 0, 325. And our second candidate is right here at 1.8570. And it looks like that the second one is our maximum at this minute. However, both of those numbers are not integers, so I put all of the integers that are in the feasible region, and I'm gonna check which one of them would give us our maximum value. So let's start the slider again, and I'll stop at each value. So right here we have 11, and as we keep sliding up, we see that z value is getting bigger and bigger. And we find out we can see that our optimal maximum value for z is 33 at 0.3, which is not very close to our original value that was close to 20. So going back to the paper, we can see that we have the same right here on the graph. And as we said, our biggest value was at 13/7. And we also saw that if we round that value to 20, this was not even in the feasible region. So then, if we go down for that point, our next guess should be 10, which we saw from Desmos that it was not even closer to the actual maximum integer variable value, which was 0.3. It was actually, I think, about 11, which is much lower than the actual maximum. So looking at the next example, we see that by using Torah, the maximum value is 10 when x1 is 5 halves. So originally we can choose our candidates to be 3, 0, or 2, 0. But if we plug those back into the subject to portion, we see that 2 times 3 plus 0 is 6, and it's not in the feasible region. And then also, if we plug in 2 times 2 plus 0, it's not equal to 5. So both of those are not in the feasible region. So let's look at some more examples on the next page and see how to actually formulate those, and we can use integer programming. So the first problem gives us an option of buying stocks and then having a return on the stock. So our variable, I'll call it xi, it will mean that we bought stock I, where I is between 1 and 4, and it's a binary variable, so if we bought the stock, the value would be 1, and if we didn't, it will be 0. And we want to maximize our return, so for each of them, we have for the first one, return of 16 if it was made, a return of 22 for the second one if that was made, a return of 20 for the third, and 8 for the fourth. So we want to maximize that number, subject to the restriction that we do not have enough money to invest in all of them. So we can only invest 5,000 for the first one, because this is the price of the first one. The price of the second one is 7, respectively 4 and 3 for the third and the fourth. And all the money that we can spend is actually $14,000. So using integer programming, we will plug this into Torah and see what the optimal solution is. So going into Torah, we see that we have 4 variables and 1 constraint. And again, I want those to be binary. That's why I set lower and upper bound 0 or 1, and also they are integers. That's why I set them into integer programming. And we actually get 2 solutions. The first one yields $36,000, and the second one gives us $42,000. So we'll go with the second one, which would give us a return of $42,000, or a profit of $42,000 when we are making investments 2, 3, and 4. So let's start on the next question. It says that we have 7 full wine bottles, 7 half full wine bottles, and 7 empty bottles. So my variable would be Bij for bottles, and with I will denote the ith person. So we have 3 people, so the I value can be 1, 2, or 3. And J would be the type of bottle each person receives. So respectfully, J equal to 1 would mean that the each person get a full bottle of wine. J equal to 2 would mean that they got a half bottle of wine. And J equal to 3 would denote that the person got an empty bottle of wine. And let me just finish typing all this. And I would like to maximize the number of full bottles that each person gets, because there is no point to send somebody out with 14 half bottles when they can get 7 full bottles, if that makes sense. So here is gonna be my constraints. The first one is gonna denote that everybody gets 7 bottles, since these 21 bottles and we divide them to 3 people. So everybody gets the same amount of bottles, means everybody would get 7 bottles. So writing them down, I do BI1 plus BI2 plus BI3 equals to 7, which would mean we have 3 cases. Again, I is 1, 2, or 3. So if we plug in 1 for I, we'll have that the first person got B11 would be the first person, the number of full bottles that they got, plus the first person, the number of half bottles that he got, and BI3 would be the number of empty bottles. So for the second equation, I'm writing B1J plus B2J plus B3J equal to 7, which would mean that each type of bottle equals 7. And by type of bottle, I mean a full, a half, or an empty bottle. So looking into it, the first person got full bottle, the second person got full bottle, the third person got full bottle. The total of the full bottles equals 7. And again, we do this for half and for empty. So that's again another 3 equations for each of the J's. And our last equation would be to make sure that each person gets the same amount of wine, which is denoted by each person gets a full bottle, which would be just BI1, plus each person gets half of a bottle, the liquid in a half of a bottle, and the third term, 0 times BI3 would mean the person gets a bottle, but it's empty, there is no wine in it, and that must equal 3.5. And in a second, I will explain to you where I got 3.5 from. So it says that there is 7 full bottles and 7 half bottles. So if we add all those together, we have 7 full plus 3.5 full from the 7 times half bottles. That is total of 10.5 bottles of liquid, if we want to put it this way, or bottles of wine that are full total. So if we want to divide this among 3 people, we have 10.5 divided by 3 equals to 3.5. So this is the amount of wine that everybody would get. However, it doesn't need to be in full bottles. It can be some full and some half bottles. So based on all those restrictions, we just need to denote that Bij needs to be bigger or equal to 0, and it needs to be an integer, because we don't want to give people broken bottles. So based on this, we're gonna have 3 equations for each of our constraints. So that would give us total of 9 equations or 9 constraints, and we also have 9 of the variables for each I and j. So I'm plugging it in into Torah. Again, 9 variables and 9 constraints. And I am maximizing the number of full bottles that each person gets, because it will be silly to give somebody 14 bottles that are half full instead of giving this person 7 bottles that are all full. So I plugged in all the numbers, and I will just keep it here for a few seconds just to see what did they put for each of the constraints. And again, we are doing integer programming. We don't want to have broken bottles or parts of bottles given away to people. And I am just checking my numbers to make sure I did not make a mistake. So here is our solution. And I'll put it back on our paper and summarize what that it means. So basically we found out that the first person would get 1 full bottle, 5 half bottles, and 1 empty bottle. And then the second and the third would get the same thing, which would be 3 full bottles each, 1 half bottle each, and 3 empty bottles each. So let me just type this in, and then we'll double check if everybody got the same thing. So if we look at the first person, he got total of 7 bottles, and then 1 plus 5 times half is 3.5 total. So the first person got 3.5 full bottles and 7 bottles total. And the second and third person each got 3 plus 1 plus 3 is 7 bottles total and 3.5 bottles filled with wine. combined. So everybody got the same amount of full and bottles and the same amount of wine. So this is the final solution. Thank you for watching this video, and I have another one coming for week 7 Wednesday assignment. Thank you.